All right. Afternoon, everybody. My name is Jason Whitehead. I'm the Associate Department Head for Physical Sciences here at Wake Tech in Raleigh, North Carolina. We'd like to welcome our STEM speaker today, Dr. Wendy Brown, brought to you by the Equity in STEM Club at Wake Tech. If you're interested in STEM outreach, careers, and initiatives, contact me for more details at jrwhitehead@waketech.edu. I will put that information in chat also. Dr. Wendy Brown graduated with her doctorate from UC Davis and is a current Translational Postdoctoral Fellow at UC Irvine. And she's heavily involved in outreach promoting women in STEM. Fun fact, she also served as a professional cheerleader for the Oakland Raiders, the Sacramento Kings, and the Atlanta Falcons. So following this talk, we'll open up for Q&A period. Join us in live chat by signing into YouTube. At this point, I'm going to hand things over to Dr. Wendy Brown, who's going to talk to us about the future of medicine.
Okay, hi everyone. Hopefully you can hear me okay. I'm going to show a quick PowerPoint, basically what I call engineering the future of medicine in more ways than one. So give me a second here. Just make sure everybody can see that. Okay, so like I said, this presentation I'm titling Engineering the Future of Medicine, and hopefully you'll see kind of more than one way where I'm going with this. Just a quick background on me. I grew up in State College, Pennsylvania. It's basically the exact center of the state in Pennsylvania, right where Penn State University is. My dad was a professor there until a couple years ago when he retired. And this winter probably looked something like this in State College, so that's why I moved. I moved to Atlanta, where I went to college at Georgia Tech. I got a Bachelor's of Science degree in Biomedical Engineering, graduated in 2011. And then while I was there, I also cheered for the dance team. We were called Goldrush. And finally, my last year in college, I cheered for the Atlanta Falcons. Then from Georgia Tech, I came to UC Davis in Northern California, Davis, California. It's about 20 minutes outside of Sacramento to get my Ph.D. also in biomedical engineering. And you can see I'm very excited about finally finishing that. And then while I was in grad school, I cheered for the Sacramento Kings. And then I did 4 years with the Oakland Raiders. My last season was the football season that ended in 2016. So here I am now. I'm a translational postdoc at UC Irvine, and it's a traditional postdoc in the sense that I'm still continuing my training as a researcher and scientist, but the translational aspect focuses on learning about technology transfer and commercialization of products. We're very lucky here at UC Irvine that they have a very friendly culture to entrepreneurship, and so I'm learning everything I can about that, and whether or not I'll actually get a patent or start a company out of it remains to be seen, but definitely a valuable skill set that I definitely didn't have before. And then also, because of my science and my cheer experiences, I'm also part of an organization called the Science Cheerleaders. We are an organization of over 300 current and former professional cheerleaders with degrees and careers in STEM fields. And we basically try to playfully challenge stereotypes and encourage involvement of what we call citizen scientists, or people who are just interested in science, in real science, through our sister site, SciStarter. So if you're interested in checking that out, definitely go to SciStarter. They have a lot of really cool experiments that are basically crowdsourced. So they're real experiments, real grants that need crowdsourced data, like measuring rainfall or tracking butterflies or anything like that. It's real cool stuff. And then through Science Cheerleaders, we also do a lot of outreach, kind of like Jason said, targeted at getting kids and specifically young women interested in science. I personally really relate to our mission because science for me can be really intimidating. Not so much anymore, but you know, when I was younger, it seemed really, really intimidating. And kind of a turning point for me was when I met a role model I felt I could relate to. I was a dancer in college and, you know, struggling. Like I felt like I didn't belong at an engineering school, even though, you know, I was taking the classes and getting good grades. And finally, I met a physician who had a chemical engineering degree from Georgia Tech. I interned with her. And she was also the feature twirler while she was in school there. And then went on medical school and was Miss Georgia while she was in medical school. And I just saw her as intelligent and beautiful and successful and had a great family. And I realized that women, I could be whatever I wanted to be. And she was just a really good example of that for me. So I try to kind of instill that into other people through Science Cheerleader. So that's me. Okay, so moving on a little bit to my research. What is biomedical engineering? I'm sure a lot of you guys know, but I'm gonna break it down in a way that made sense for me. So let's break down the word. Bio, biology, medical, medicine, engineering. Biology is the study of living organisms. Medicine is the science practice of the diagnosis, treatment, and prevention of disease. And engineering is the application of science and mathematics to make the properties of matter and energy useful to people, or in short, the design and manufacture of complex products. So biomedical engineering is really a combination of everything. The application of engineering principles and design concepts to medicine and biology for healthcare purposes. So in my mind, biomedical engineering is engineering anything to help medicine help people. This can include a wide range of specialties. There are more out there than just the ones I'm going to list, but these are kind of the ones that come to mind when I think about it. So first, biomedical imaging. So engineering the technology and the machines to see inside the body, visualize structures without actually opening somebody up and going inside and looking at it through eyeballs. I personally think medical imaging is really, really cool. I don't know anything about it, but it just like amazes me that we are able to see the detail and like the structures that we can see inside the body. I actually just got an MRI on my jaw because I have TMD. Everybody has TMD. And it was like amazing to see like my own jaw and my eyeballs in my head. I just was amazed by it. Next, biomaterials. So for example, those that go into these metal and plastic or ceramic hip replacements, this is kind of what some biomaterials might look like on a micro scale. Basically engineering materials that will be in contact or be within the body. Sometimes those can be bio-inert, so they don't do anything, biocompatible, they can chill in the body and be fine, or sometimes you want them to be bioactive and actually elicit some sort of integration or healing response inside the body. Bioinstrumentation, so teeny tiny little sensors that are used to measure things on the body. This, for example, is out of a research group here at UC Irvine, and this is a blood pressure sensor that you can wear continuously, and it will continuously monitor your blood pressure so you don't have to wear a cuff constantly. Biomechanics, this is actually research out of a lab that one of my friends did her PhD in at the University of Delaware. So this specialty focuses on tracking human motion and studying human motion and injury a lot of times. So in this particular figure, this research group mapped a figure skater as she was skating, and this is her landing a jump, and then the skeleton on top is actually her mid jump. But so they mapped her motion, and basically they were studying the motion of these figure skaters so that they could give them feedback to make their skills better and also to help them prevent injury. Another specialty is drugs and drug delivery. So for example, AIDS medication, anti-cancer medication, sickle cell medication, fabricating the drugs, and also looking at the delivery of these drugs so that they're targeted and they do exactly what you want them to do and not what you don't want them to do. cellular, molecular, and genetic engineering. So this is where you start to talk about like the CRISPR-Cas9 stuff or gene editing. A lot of cancer therapies also focus on like gene editing type stuff. It's kind of a cool futuristic schematic of gene editing right there. And then tissue engineering is what I do. So this picture is a ghost heart, people call it. It's a real heart that grew in probably a pig's body. And researchers decellularized it. So they took out all the cells, hoping that that would remove any of the material that would cause an immune reaction. And then the idea is that you would be able to ghost heart with a patient's own cells. However, I have other things to say about that. Remove cells doesn't remove all the antigens. My lab actually published a paper on that a couple of years ago, but I mean, I think it's amazing that they were able to preserve the structures like they did. Anyway, if you have questions about that, ask me later. So anyway, I think in general, biomedical engineering is so broadly defined. Obviously, it incorporates principles of mechanical engineering and electrical engineering, chemical engineering, biology, medicine, everything. So it's very broadly defined, and I think that is the sky is the limit. It's a relatively new field in terms of defining it as biomedical engineering. It's kind of always existed, but just hasn't had a name to it. But really, I love biomedical engineering because it is literally the future. Like, we are forging the path of a lot of these devices and instruments and technologies to help people. And growing up, I have always been fascinated with the human body, but I didn't want to just study it. I also wanted to engineer things that helped people. And so biomedical engineering was the perfect fit for me. So moving on to my research a little bit, you guys all probably know somebody that has osteoarthritis. It's a painful degenerative disease that affects both the cartilage and the underlying bone. So you get cartilage degeneration and also bony overgrowth, and it can be very painful. It affects 20 million Americans at an annual cost of $60 billion to the healthcare system, so it's a huge problem. 12% of osteoarthritis is post-traumatic, or basically occurs because somebody has sustained a cartilage damaging injury. Essentially, cartilage doesn't heal because it doesn't have a blood supply and therefore doesn't have access to nutrients or stem cells. So if you have an injury, it'll pretty much only get worse. And a lot of those injuries, if they're left untreated, will degenerate into osteoarthritis, and then people need total knee replacements. And then something that's very personal to me, because I have a lot of friends and family in the military, and my boyfriend's a pilot in the Marine Corps. Post-traumatic osteoarthritis is a primary source of disability for military veterans because of high energy impacts like car crashes, plane crashes, or IED explosions. And so, like I said, you know, injuries are a huge kind of like impetus for osteoarthritis. And if you sustain a cartilage damaging knee injury, you're 7.4 times more likely to develop osteoarthritis, which is like crazy to me. That's really a lot. So basically, the motivation of my research is to repair that focal cartilage damage before it gets worse. If you can take a very, very small injury and fix it, hopefully we can stave off degeneration and prevent people from needing a total knee replacement at all. So the goal of my research is to engineer neocartilage. So it's neocartilage, it's not synthetic, but we do make it in the lab. It's made out of natural materials like cartilage cells. So our goal is to engineer that neocartilage with the properties of healthy native cartilage, the mechanical properties, the biochemical content, the structure, the shape, basically try to get it as close to healthy cartilage as possible so that we can eventually put it back into the body and fix those injuries. This is the general process we go through. I know a lot of you may not be in biology or biomedical engineering or have backgrounds in cell passaging and stuff like that, which is totally fine. Just going to break it down a little bit in case anybody's interested. So the general process we go through is taking cartilage. So this is like a femur, and this is where your knee joint would be. And there's articular cartilage that lines the surface of those articulating bones. So we chop up that cartilage and we digest out the single cells. So we basically have a slurry of chondrocytes, which are the cells in cartilage. And then I go through a purification process. If anybody's familiar with cartilage, you may question, well, chondrocytes are supposed to be the only cell type in cartilage. That's initially, back in like the 1800s, why people thought it would be easy to engineer. But it's very easy to get contaminating cell types into that cell population while you're isolating it. So for example, all of the surrounding tissues have a blood supply, so it's super easy to get red blood cells mixed in. And red blood cells actually cause death of chondrocytes. So I showed that if you can remove those red blood cells and other contaminating cell types, basically the chondrocytes do a lot better. So I take those pure chondrocytes and then I plate them into a flask. So they're plated in monolayer, so just one layer of cells, and then they adhere and they grow in number, they divide. And I do that process called passaging to expand the cell number. I do it 3 times and then release them from the monolayer, and I have a larger population of cells now. However, the difficulty is that when chondrocytes are in a 3-dimensional tissue, cartilage, they like to be in 3 dimensions, and when we adhere them onto a monolayer, they forget that they're chondrocytes. They start to act more like fibroblasts. So they kind of forget who they are and they start making really bad cartilage. And so we put them into this aggregate redifferentiation step. It's a suspension culture where the chondrocytes can't adhere to anything and they basically like can't grab onto stuff and they bump into each other and they're like, whoa, you're kind of a chondrocyte, so am I. Oh my gosh, wait, we're chondrocytes, let's make good cartilage again. I imagine the conversation that's happening. So after this aggregate redifferentiation step, I take out the single cells again, and then I seed them into this neocartilage self-assembly where, again, the cells can't adhere to anything, and they therefore maximize their cellular interactions and minimize the free energy in the system. Basically, they just make cartilage in the body, out of the body, sorry. They make cartilage out of the body pretty much in the same way that they do in the body. So then at this neocartilage self-assembly step, we can add chemical stimulation or other mechanical stimulation. So we can like squish them or stretch them, stuff like that, to make that neocartilage as similar to healthy native cartilage as possible. So this is what a neocartilage construct looks like. This is 5 millimeters, so it's about the size of a dime. This is what we engineer every day for our studies. I actually think it looks pretty good. It's pretty smooth and flat and crunchy. We have this crunch factor we talk about. If you make good cartilage, it'll crunch when you like punch a hole in it or cut it, kind of like native cartilage. Obviously, we do quantitative assays because we're engineers, but this is a large construct we engineered. So you can see this is the size of a quarter, and we are bigger than that. So that was pretty cool. And then taking that large construct, I was able to make an osteochondral construct. So this is a 10 millimeter scale bar. So you can see this is a pretty big construct. It's maybe about that big. And it has a ceramic kind of thing on the bottom. I hesitate to call it a scaffold because we don't use scaffolds in our tissue engineering process. It's something that makes us very unique. We just only use cells. Sometimes we can add the signals, but if you guys have ever seen the tissue engineering triad, it's always cells, signals, and scaffolds. But we do it with just cells, and then sometimes we also add the signals. But this ceramic portion basically facilitates bone ingrowth. So this construct is in the shape of a condyle. So this is the end of your shin bone where your knee meets your knee meets. So where the shin bone meets your thigh bone. This is the end of the thigh bone. It has these 2 nubs called condyles, and so this construct is in the shape of one of those condyles. Shape and size actually of one of those condyles. And you can see the cartilage on top and then the ceramic portion on the bottom. So this talk is about, engineering the future. So for me in my research in cartilage, where do we go from here? Right now, people take knee cartilage to make knee cartilage. So people are essentially robbing Peter to pay Paul, basically. If you can fully repair an injury, then that's great, but you're still making a new injury in that person's knee, so that's kind of defeating the purpose. So in my mind, the future is using something like rib cartilage. So rib cartilage is used all the time in plastic surgeries, for example, like fixing noses and ears or tracheas, stuff like that. And you have these floating ribs kind of in your back that are frequently used to harvest cartilage from. So if we can take rib cartilage and turn it into knee cartilage, that's way better than robbing from your knee. And then if that works, you can go to hip cartilage from rib cartilage, ankle cartilage, jaw cartilage. You have a little kind of like a mattress of cartilage in between your jawbone and your skull called your MJ disc. And that causes a lot of problems for a lot of people like me. Also nose cartilage or ear cartilage, you know, basically ways to fix people's cartilage injuries in the least invasive way and least damaging way possible. And then from there, we can talk about large and shape specific implants. So I kind of showed that condyle picture, but ultimately we would want to be able to engineer the entire end of your thigh bone. So this is a metal implant from like a knee replacement. But imagine if we could engineer that in cartilage and bone and have a bioprosthesis basically instead, or an ear. A lot of people are actually born without ears or sustain like substantial damage in their lifetimes. And so if you could just take a scan of a patient's ear on the other side of their head and then engineer them a new ear and implant it, the quality of life for those people would go up extraordinarily. So now shifting gears a little bit, I want to talk about women in science because to me, this is engineering the future of medicine in a different way. So looking at participation in STEM sort of oriented classes in kindergarten through 12th grade, you can see for the people that took pre-calculus and calculus, 37% of those people, 37% of women take calculus and pre-calculus classes. 34% of males take those classes. 50% of women take advanced biology, 39% of men take advanced biology, 36% of women take physics, and 42% of, sorry, I don't know if I said women, 36% of women take physics and 42% of men take physics. So you can see, I mean, ultimately, I think we'd all like to see this be 100% of women take these classes and even 100% of men take these classes. You can see biology is more popular than like physics, for example. And then looking at this figure, this is the percent of high school graduates who report interest in math and science by gender, and this is from 2009. So let's look at the females in the light blue. So 53% of females say they like math. However, 43% say that math is one of their favorite subjects. 59% of females say they like science, but only 34% of females say that science is one of their favorite subjects. And I don't know about you guys, but like I said earlier, I think, at least back when I was in high school and stuff, science could be very intimidating for me. And I always thought that science and biology and physics was really interesting, but I struggled feeling like I could keep up with it. And so I think that that's kind of where this discrepancy lies between saying you like science and it being a favorite subject. So yeah, let's move on to percentage of degrees earned by women in post-secondary institutions from 2008 to 2009. So let's look at biology and biomedical sciences. You have 59% of those degrees awarded are bachelor's degrees awarded are given to women. But then let's look at engineering and engineering technologies. So this is stuff like civil engineering or mechanical engineering, and we're down to 16.5%, which is pretty low. And then So you can see master's and PhD. Fortunately, in the biology and biomedical sciences, that percentage is like actually pretty well maintained. However, looking at physics and science technologies, you can see that percentage starts to drop off, and same thing for math and statistics. So right now, you know, well, let's look at more recent data too. So here is the same information from 2014 to 2015. So biology and biomedical sciences were about the same, which is great. Haven't lost anything. The physics and engineering and math look like they've gone up a little bit. But again, with math and statistics, when you go from bachelor's to master's to PhD, very, very few women are pursuing advanced degrees in that area. So it's really an issue of retention almost. And I recognize not everybody is going to get a master's and not everybody is going to get a PhD. But ultimately, we want those options to be available and appealing to women. So I'm not sure if you guys have heard of the Draw a Scientist test. There have been some articles floating around the internet lately, because a newer version of that study was published. The original study was published in 1983. And basically, researchers asked students to draw what they thought a scientist looked like. And in 1983, they analyzed all of these pictures and tests that had been drawn in the 60s and 70s. And of 5,000 students that drew the scientist, only 28 of those students drew the scientist as female. That's less than 1% of those students. And interestingly, only girls were the ones that drew the scientists as females. None of the boys drew female scientists. Also, there's research that indicates that younger children are more likely to draw female scientists. So at a young age, basically girls draw scientists as women and boys draw scientists as men. Kind of makes sense because it's what they can relate to. But there's a change in perception that happens around age 8, where most children, boys and girls, start to draw scientists as men. And so that's probably the age where they're becoming a little bit more aware of these social stereotypes. However, like I said, there's a recent version of this study that analyzed more recent drawings, and now 3 in 10 children are drawing scientists as females. So that's 30% of kids. And that's, you might say like, oh, 30%, but that's more than ever, which is great. All right now we're hoping for is progress. And this is an example of one of those drawings. I just like it because it looks like me. Has green eyes and red hair. And she looks like she's a paleontologist looking at dinosaur bones, which is pretty cool. So again, more draw scientist type stuff. You can see on the left a balding old man with glasses and a lab coat and an Erlenmeyer flask or a beaker of something steaming in green. So basically a mad scientist. And in this particular case, these teachers asked students to draw what they thought a scientist looked like before having any knowledge or experience or any like enrichment activities. And then these teachers brought in a lot of scientists, both men and women, to talk about their careers and their research and stuff like that. And then at the end, asked students to draw what they thought a scientist looked like afterward. So you can see the after pictures. We have a very friendly looking woman. Yay! And we also have another woman here looking up at the stars, which I think is great. And it just really emphasizes the importance and the impact of outreach and mentorship. And even with kids at a young age, you know, you may not be able to like mentor them because they're not in real science type classes, but just serving as an example is so important. And this is why I do science cheerleader stuff. This is at the Science and Engineering Festival in 2014. So I do that with the science cheerleaders. It's happens every 2 years. We perform science-themed shows and outreach activities and stuff like that. And then this is me representing the Raiders at a more local science and engineering festival. And I just love this picture. That little girl is so cute. She was so excited. Warms my heart. So let's look at some statistics over time. This is from the NSF. this graph is like a little bit crazy, so I'll just walk you through it. So on the x-axis is year, and on the y-axis is percent of its participation of women in these specific fields. So we're looking at the red lines here. The solid red line is biosciences bachelors. The dashed line is biosciences masters, and then the like super tiny dashed line is biosciences PhDs. So you can see that the increase in bioscience masters for women has increased kind of at an earlier time point. Then the bioscience masters, which is this dotted red line, increases a little bit after that. There's almost like a lag time. And then there's also a bioscience PhD line, this red one, which has a much slower increase, but it is on the rise. So to me, the explanation for this is that outreach and mentorship is definitely successful, but we are targeting women at a young age, which is great. It's definitely needed, but it just takes longer to get to a PhD level just by age, and not as many people pursue PhDs or master's degrees in general. So we're seeing that bulk increase earlier for the bachelor's, and then it's trickling over to the master's, and then it's trickling over to the PhD level. So like I said, again, engineering the future of medicine in terms of equity. So I think the most important things that we can do to ensure this happens is, number one, to recognize that science is hard, and that's totally okay. It's supposed to be hard. Anybody who tells you it's easy is lying to you. I am not a particularly fast learner. I have to put in a lot of time and a lot of work on my own, and that's totally okay. I always tell people, like, you're not born knowing calculus. You're not born knowing how to walk either, but I bet at least some of you have run marathons. And a day out of the womb, you're not thinking, oh man, after I run that marathon, it's going to be so hard. You're just taking it one step at a time. And that's what we all should be doing with our science and engineering courses and careers. Take it one step at a time. And if you don't know something, that's okay. You're not supposed to know it. Just put in the work, just like you practiced walking, practice this field, this topic, and you will get better. That was the biggest realization, I think, for me in terms of like being able to be successful. It's okay that stuff is hard. You'll get it. And then don't preach it, live it. I mean, obviously preach it, but don't just preach it. And I recognize that I'm kind of preaching to the choir here with this particular group, but it's great to talk about science and equity and opportunities for women, but the change comes from people actually living it. The women in science fields showing other women that they can do it too, or you know, making other people in their company aware that women are smart and can handle the job. Definitely strive to be an example for other people. I kind of talked about this earlier, be an example for little kids. You know, mentorship or like outreach and stuff may not be appropriate for kids that are super young, but just having them see a female scientist that they can relate to is so meaningful. I judged a science fair, actually a regional science fair a couple weeks ago, and all of the teams that I judged were 6th grade girls, which I thought was like really great and like providential almost. And I remember speaking to their teacher afterward, and she said, oh my gosh, they were so excited to meet you. They said to me that they were afraid their judge would be a grumpy old man. And I remember when I walked up and I was like, hey guys, your judge, are you ready to get started? I had like smiles, and one girl went, yes. And I was like, I like you guys. And it just really like shows me how important it is that people can relate to other people, other mentors and stuff in their field. You know, hopefully those girls will continue to like science because they had a good experience, and that's all I can ask for. Kind of continuing with that, mentor young women, you know, as girls get older into high school and college, definitely seek out mentorship opportunities to continue to reinforce that other women are in these fields and they have somebody they can relate to or somebody they can look up to or ask questions to. And then kind of something that I think is one of the most important things personally for me is to support your female colleagues. Oftentimes women talk about, you know, like discrimination by men and, you know, the whole mansplaining thing, which I've definitely experienced to a certain extent, but by far the most discrimination I have experienced is from other women, which I think is really unfortunate, because again, we're supposed to be helping each other out. Nobody is gonna forge this progress in these male-dominated fields except for us. And so when you have women pitted against each other, it doesn't help anybody. Yeah. Anyway, so just be an Elle Woods. Don't be a mean girl. Support your fellow females. Not everybody looks the same. Not everybody comes from the same background or has the same experiences, and that's okay. So yeah, that's hopefully what we can do to keep things moving forward. So yeah, that's the end of my actual talk, and it's a Fireside comic that I really like because these are all scientists and they're running after an ice cream truck, which is, you know, I'm not gonna say I haven't done it before. Anyway, so thank you guys so much for listening. Please let me know if you have any questions. I'm gonna pop out of this screen share, and then I will be answering questions from the YouTube chat window. So answer your questions there. I will, I guess, keep talking to you shortly. All right. Hi, guys. Okay. I'm just getting into the YouTube chat. Hi, Ayana. I see you're here. Okay. I see Joseph. Oh, wait, lost my place. Okay, Joseph says, I'm a student in an EGR class. Is there a field where you work on nanotechnology on a cellular level to repair individual cells that have been damaged? I personally don't work on this, but I'm sure somebody does. I think that's probably more the topic of the genetic engineering aspect. But again, like I said, with biomedical engineering, the sky is the limit. And if you are interested in doing research in that area, definitely just Google it. You know, a lot of stuff will come up and lead you in the right direction. Another question from Joseph. In what ways can electrical engineers work in the biomedical field? In what ways do electrical engineers and biomedical engineers complement each other? I mean, that's a really great question. A lot of electrical engineers have overlap in biomedical engineering. All that sensor stuff is electrical engineering. And I personally don't have a background in it. So if an electrical engineer to do a project in a biomedical engineering lab, that would be great, because somebody like me who has a background in like cellular biology and more mechanics can talk about, you know, maybe the principles and what I want to do with something and how I want to measure it. And then the electrical engineer can actually build the sensor or equipment or whatever to help measure that. Okay, I'm going to skip over some more of Joseph's questions. Sorry, Joseph. I just want to try to get to some other people's questions. So Dr. B.A. Coles asks, is it harder to make cartilage for different types of joint, like the glenohumeral joint? So cartilage, there are a lot of different types of cartilage in your body. So like your ear is an elastic cartilage because it moves a lot. Articular cartilage is at the end of your articulating bones. So like in your knees and your shoulders and your hips. You also have fibrocartilages, which are kind of a more fibrous version of cartilage in your TMJ disc. and your knees, they have another like meniscus kind of in your knee between your thigh bone and your shin bone. And then you have stuff like your intervertebral discs, where that's a different type of cartilage. So my answer to that is that they're all just different types of cartilage. And they all have their own requirements that may or may not be different from other types of cartilage. So kind of like what I mentioned earlier, we strive for biomedical cartilage. And so that is basically cartilage that is mechanically the same, biochemically the same, and structurally the same as what we're striving for. So those engineering criteria are going to be different depending on what type of cartilage you're engineering. And I don't think that one thing is harder than another in particular. It's just different, I would say. Hi, Daryl. Does having knowledge of chemistry help? And if so, what types of chemistry were helpful? Again, I would say it just depends on what specific project you're working on. So for me, biochemistry is helpful because I can understand kind of the way molecules might break down or interact with other molecules. So yeah, it just depends, you know, like it's helpful to know the biochemistry of like the collagens or the gags inside the cartilage. So, oh, my chat window went away. Yeah, anyway, and then, but for example, one of my friends from when I did my PhD, he was trying to synthesize a molecule that he could use in stem cell homing. And so he loaded up on organic chemistry for like a year before he even tried to make anything. So it just depends on what your research area is. But again, it definitely doesn't hurt. The more diverse knowledge somebody has in this field, the better, I think. Okay, so I'm going to go back up to some questions from Joseph because they are all from that same class, actually. Different people in the same class. Hi, Whit. As a veteran, in what ways would the medicinal injection of device be adapted for field use and combat application for wounded, feasible and cost effective? So with the cartilage repair that I was talking about, it would not be like an immediate treatment that would happen in the field. It would be something that would happen once the patient is stabilized, obviously as soon as possible. However, there is research into molecules that basically stop the injury cascade or try to slow it down. And there's research to show that if you have a cartilage injury, that injury cascade starts immediately. So if you are skiing and you fall and you hurt your knee, right away you start to get those like very, very small changes, bad changes. So in that situation, if, you know, I think that the priority is, you know, saving somebody's life, stopping the bleeding, stabilizing them, making sure they're not paralyzed. But yeah, ideally it would be injecting some sort of like stabilizing agent to stop the degenerative process in their joints too. Okay, I think I have a question from Daniel. With the high rate of sleep apnea in the military community, would the nasal septal cartilage be beneficial for those veterans? Oh, absolutely. So I've started to focus on engineering that cartilage actually, because in my opinion, it's always been very important. A lot of focus is on the knees and the hips and the spines and stuff like that, but you do have end stage treatments like knee replacements or spinal fusions that can allow people to live long and pretty happy lives. However, if you don't have a nose or you have a not functional nose, your quality of life is significantly impacted. And I would argue that it's maybe even more impacted than if you get a knee replacement. So definitely talking about deviated septums and those that sustain facial injuries as well. I think that engineering nasal cartilage could be very, very impactful. And that's why I'm trying to do research into it. So it's a great question. Would you mind would you suggest obtaining a doctorate or an MS or a BS degree? Be okay with work in biomedical engineering? Just depends on what you want to do. With a bachelor's degree, you're more likely, I think, to be in sort of a technician position or work in industry. With a master's degree, at least in my experience, master's degrees tend to be more class-based than research-based because it takes so long for somebody to learn the skills they need to do research. By the time they learn, their master's period is almost over. But that doesn't mean it's any less meaningful. With a doctorate degree, those tend to be people who strictly want to do research and want to go on to academic faculty positions and someday run their own research labs. So I would say it just depends on what you're interested in. If you want to do industry research or work in sales for biomedical technologies or be a tech or something like that, I would say a bachelor's or master's is totally sufficient. But if you want to be a professor and teach and run your own research lab, you would almost always need a PhD. Hi, Zach. Where do you see biomedical engineering progressing in the next 10 years? 3D printing is really hot right now. And I think, like the Star Trek goal is to have a biological 3D printer that can just 3D print you a replacement part. And people are definitely working on that. Within the next 10 years, I would hope to see a lot more biological and cellular based products available to people in the clinic. So FDA regulation is kind of the big barrier to that stuff. And I'm not saying that's a bad thing because the FDA helps protect people and keep people safe. But it's just something that you have to go through the process of, and it can definitely take a while. And for example, like with the technology that I'm working on, we call it the wild, wild west in terms of the FDA, because since there are no technologies like ours that have gone through FDA approval, they don't have any regulatory guidelines for those technologies. So we're having to kind of piece together things that apply to our technology from other technologies. And there's a lot of communication that's going to have to happen between us and the FDA. So yeah, short answer to that is just a lot more cellular based products that work at an earlier intervention point in the clinic. How long did each degree take me? How did I choose my universities? How was I able to focus on research and cheer at the same time? Those are all very great questions. So my undergrad, I took 5 years because my major was biomedical engineering. I also did undergraduate research thesis, and I had minors in Spanish and organizational leadership. And I also danced every year. Also at Georgia Tech, it was just very common for people to take 5 years. We joked that graduating in 4 years was like leaving a party at 10 p.m. So it was just more common to take 5 years, and I didn't want to like absolutely kill myself with coursework. I wanted to like enjoy college a little bit. So I took 5 years with that. My PhD took almost 6, which I think is not super common. But again, I was cheering every single year of my PhD, and I was really lucky that I had a supportive advisor who thought it was awesome that I did that as long as I was continuing to get work done. But there was definitely a little bit of a trade-off there in terms of time. And then how was I able to focus on both? For me, kind of one thing was an escape from the other. So, I would work all day in lab and I would be exhausted, and then I would go to practice and I would see my friends and I would dance and I would get exercise and feel really good, excited about the games and stuff. And then when I was physically tired, I would, go back to the lab and do research. And I actually drove from Sacramento to Oakland and back for 4 years for practice. And I found that those long drives were some of the best times to think about my research problems, stuff that I was like really stumped on. And I would like take voice notes, like Google search this thing to look up later. So for me, it just worked out that they were complementary, and kind of like I alluded to earlier, dancing is definitely a skill. Learning dances takes time. You don't walk into practice knowing a dance. So having that experience of learning a new dance, having to practice it, and then performing it was just reinforcement that everything is a skill, including coursework and material that I don't know. So again, if I don't know something in a class or I'm having trouble with something, it's okay. Just keep working at it. Okay, so we have about 5 minutes left. So I'm gonna look for some more questions that are maybe different topics. Biomedical field has experienced tremendous growth in the last few years. Do we feel this is a bubble or it's going to continue? Definitely going to continue, I hope. More researchers, hopefully more funding for research. People are not getting younger, you know, baby boomers are getting older, and so people just, they need more stuff. And as science advances, we continue to stand on the shoulder of our predecessors. What would I recommend for further education after a bachelor's in biomedical engineering? For somebody interested in biomaterials or tissue research? I would say, like, think about how much you like research and decide if a PhD is something that you want to do, or maybe start to look at career options that don't require advanced degrees and see if the jobs entail something that you want to do, or if the jobs that you would aspire to do require more advanced degrees. But you can also take seminars all the time to learn more in different areas and figure out kind of what you want to specialize in. Can't decide whether I major in computer engineering or electrical engineering. How will I know which is a better choice for me? I don't know if it's possible for you to talk to other students in those majors, but I would definitely say, like, talk to your peers if you can, and maybe even talk to people who are in jobs that you might want to do someday and ask what their background is or what their major was, and if they thought it was good or, you know, they should have done something differently. Do you think progression is possible from cartilage to other parts of the body since organs are specific to the person's blood type and the antibodies? So cartilage is actually, we call it immunoprivileged because it doesn't have blood supply. It doesn't have access to a lot of those cells that cause an immune response. We do have research that shows it's not as immune privileged as everybody thinks it is, but people receive cartilage transplants, allogeneic cartilage transplants, so cartilage from somebody else into the patient all the time, and they don't receive immune suppression drugs, and they can live like that the rest of their lives. You said replacing cartilage from the knee to replace injured cartilage isn't helpful, counterintuitive to my goal, but you wouldn't use rib cartilage cause the same problem? What makes it different? So just to clarify, my point there was that, so if you have a cartilage injury in your knee already, you don't want to cause more damage in your knee to fix that first injury, because now you basically have injuries in your knee, or 1.5 maybe, because you kind of healed that first one. And your knee is very mechanically loaded, so it has a higher chance to degenerate, versus like your rib cartilage, specifically your floating ribs. They're used all the time in procedures, you know, plastic surgery procedures, like you said, and they don't cause significant impact into people's lives because it's not a super load-bearing region. So it's just looking for an alternative source of cartilage that can give you the same end goal for in the knee or another part of your body, but with less impact to the patient. Go Raiders! Ah, thank you. What are the most rewarding career options for somebody in biomedical engineering? What are the most rewarding career options for someone with a BS in chemical engineering, in my opinion? I think it just depends on what you want to do. I know a lot of chemical engineers go into like oil and petroleum type stuff like that, or you know, like, I don't want to like use the wrong word, but like process management in terms of like creating like chemical stuff. I actually have a friend who did her PhD at Davis with me in biomedical engineering, and she was a chemical engineering undergrad. So there's definitely crossover possible, but I think most rewarding for me is most fulfilling. And so that, again, for me is feeling like I am helping people or making some sort of like impact, positive impact in society. And so for me, that's just tissue engineering, and I'm a weirdo that's always been interested in cartilage. So I would just ask yourself like what your ultimate goals are and what you will find most fulfilling that can simultaneously pay your bills. Was I on the team, the Raiders team at the same time as Angela Johnson? No, I wasn't. She cheered, I think, quite a bit before me, but I've actually gone to some of her comedy shows and met her, and she's hilarious and like really cute and nice. So yeah, I think that's about all the questions and time to wrap up. So thank you guys so much for listening in. Hopefully you got something out of this. I really appreciate you listening, and yeah, keep mentoring people, keep serving as examples to young kids, keep supporting each other in science, and yeah, hopefully I will see you in the future in your publications doing awesome and great things. Thanks, guys.